Now that you are fully caught up on the properties and behaviors of exponential and logarithmic functions, we are ready to look at the derivative techniques. Derivative rules for y equals e to the x and y equals the natural log of x. We write d dx of e to the x, which is red, take the derivative of the function to my immediate right, is equal to e to the x. This is worth memorizing. And d dx of the natural log of x. This is red. Take the derivative of the natural log function is equal to 1 over x. And this is also worth memorizing. I put a little heart symbol there because in French, to memorize translates literally into know by heart. Example 1.8.1, find the derivatives of the following functions. A, g of x equals 5 e to the x minus 7 times x cubed plus the ln of x. To find the derivative, we begin by writing g apostrophe x, this is read g prime of x, or the derivative of g. Using several of the rules we now have, we'll have constant of the 5. The derivative of e to the x is just e to the x, minus the constant of 7 times the derivative of x cubed as we bring down the 3, x to the power of, and then 3 minus 1 would just be 2. And the derivative of the natural log of x is a new rule we just learned, and that would be 1 over x. When simplified, we would have g prime of x is equal to 5 e to the x minus 7 times 3 is 21 x squared plus 1 over x. If you choose to, you may write that as x to the minus 1 as well. Let's do b. G of x equals 7 over x plus 10 times e to the x. We have to do an algebra step or two first, so let's look at the first term of 7 over x. I'll separate that into the product of 7 times 1 over x, and we still have plus 10e to the x. And then using the rules of exponents, we'll write g of x equals 7 times x to the minus 1 plus 10 e to the x. So when you take the derivative, g prime of x, we have the constant 7 times, and then the power we bring down is negative 1, x to the power of, and then you have negative 1 minus 1, which will actually be minus 2, plus for the next term the constant 10, and then the derivative of e to the x is just e to the x. Let's simplify a little bit, and you get g prime of x equals 7 times negative 1 would be negative 7 times x to the power of negative 2, and then plus 10 e to the x. Part C. Find the derivative of g of x equals negative 8 times ln of x. So we'll use some properties combined. G prime of x is equal to, the constant times a function rule tells us we have the constant negative 8, and then the function, the derivative of the natural log of x, is 1 over x. So we could clean this up and write g prime of x is equal to negative 8 divided by x. Example 1.8.2. Differentiate the following. Part A, f of x equals the natural log of the quantity x to the 4th. In order to find the derivative, we're going to first use a properties of logarithms to simplify. That is, we'll write this as f of x equals, and then 4 ln of x. We're using the property that lets us write the exponent as a coefficient. Now we can take the derivative using two differentiation properties. The constant times a function rule, let me go ahead and write f prime of x, and the rule for the derivative of the natural log. So we'll have the constant 4 times the derivative of ln of x, which is 1 over x, and so when simplified we'll have the derivative of f with respect to x is 4 divided by x. Let's do part B. Y equals the natural log of the quotient x divided by e to the x. We will use the difference property for rewriting a logarithm. So I will re-express this as y equals the natural log of x minus the natural log of e to the x. We've got another simplification we can do, and that is we can write this as y equals the natural log of x, and then ln of e to the x, recalling one of the properties we've had, is just x. Now we're ready to take the derivative. We'll write y prime equals the derivative of the natural log of x is 1 over x minus the derivative of x is just 1. Example 1.8.3. Find the equation of the line tangent to the function f of x equals e to the x at the point 1, e. Draw the tangent line on the graph of f of x equals e to the x. Recall that in order to get an equation of a line, you need 3 pieces of information. You need a point, a slope, an equation form of the line. The point is already given to us, so we'll go ahead and mark point. And that is the ordered pair 1, e. Next, we'll need to compute the slope, and the value of the slope is the derivative of the function evaluated at x. So we want the derivative of the function at 1. If f of x equals e to the x, then the derivative f prime of x is also equal to e to the x. We'll evaluate this derivative at 1, so f prime at 1 is equal to e to the 1, which is e. That is the slope of this tangent line. You have a point, you have a slope. Now you need the equation form of a line. The equation form we use is y minus y1 equals the product of m, which is the slope, times x minus x1, quantity. Let's replace some of the variables with the values. So we have y minus y1 is given in the statement of the problem as e, equals the slope, which we also computed, and that is e. Then we have x minus the x sub 1 value, which is 1. So let's solve this for y, and we have y minus e equals e times x minus e. We can add e to both sides, and the equation you get is y equals e times x, not e to the x, but e times x. And then we can sketch the tangent line as it touches the point of the curve at 1, e, and it has the y-intercept at the origin. The derivative rule for exponential functions of any base. It is defined as d dx of bx is equal to the natural log of b times b to the x. This is a formula you need to memorize. Example 1.8.4. Differentiate the following. A, y equals 8 to the power of x. We will apply the derivative rule for taking the derivative of any base to compute the derivative. We can say dy dx, that's using Leibniz notation, is equal to, and directly applying the formula, it will be the natural log of 8 times 8 to the power of x. Let's do this again for part B. G of x equals 4.3 to the power of x. Finding the derivative, we'll use the notation g prime of x is equal to, and then apply the rule for finding the derivative of an exponential function of any base, and we'll have the natural log of 4.3 times 4.3 to the power of x. Example 1.8.6. The estimated resale value R in dollars of a company car after t years is given by the function R of t equals 20,000 times the quantity 0.86 to the power of t. What is the rate of depreciation at t equals 1 year and after t equals 3 years? Note, Rate of depreciation means you are looking for a rate of change, and rate of change tells you that you are looking for the derivative. So we must first find the derivative function. We will write r prime of t equals, and then using the properties of differentiation, we have the constant of 20,000, and then we need to multiply it by the derivative of 0.86 to the power of t, which is the natural log of 0.86 times 0.86 to the power of t. Now we need to compute this at t equals 1. So, using your calculator, compute r prime at 1, which would be 20,000 times the natural log of 0.86 times 0.86 to the power of 1. Key this into your calculator, and the output is negative 2594.153713. What does this mean? It means that after year 1, the car is losing about $2,600 in value per year. Let's do this for t equals 3. We already have the derivative function, so take the existing derivative function and instead of at 1, evaluate it at 3. So in your calculator, compute 20,000 times the natural log of 0.86 times 0.86 to the power of 3. Compute in your calculator and you get approximately negative 1918.636087. What does this mean? It means that after year 3, the car is losing about $1,920 in value per year. You can also solve this problem using the numerical differentiation feature of your TI-84. To use that feature, press the Math button on your calculator and then scroll down to number 8 where it says NDeriv. Select the number 8. Now, for the first blinking box, put in X, and so you can choose it on your calculator. And then in the parentheses, key in the actual function, not the derivative, but the function. So key in 20,000, that's 20,000, times, and then for the exponent, 0.86, and then to the power of, the variable is x. For the first problem, we want to numerical differentiation for time equals 1. So scroll to the lower bar, x equals blinking, key in 1, and press enter. Notice that your calculator not only computed the derivative, but it evaluated it for you also at the desired time. Now for year 3, capture, that is, use the scroll button till it highlights the function you've already keyed in. Press enter. Scroll back to where the 1 was, and replace it with 3. Press enter, and you got the output. Either method is perfectly fine for this class. The derivative rule for logarithmic functions of any base, that is, d dx of log base c of x is equal to 1 over the natural log of b times 1 over x, which can be simplified to 1 divided by x times the natural log of b. Make sure you know this by heart as well. Example 1.8.7, differentiate the following. A, y equals log base 2 of x. Let's apply the rule we just learned. The derivative would be y prime equals 1 over x times the natural log of the base, which is 2. Let's do this again for part B. That is, g of x equals negative 7 times log base 10 of x. The log is understood to be base 10. If it is helpful for you, go ahead and write g of x equals negative 7 log base 10 of x. Now we're ready to take the derivative, and we would have g prime of x is equal to, the negative 7 is a constant, it stays put, divided by x times the natural log of the base, which is 10. Exercise 1.8.8. This is a completed example in your notes. Find the equation of the tangent line to the function g of x equals 5 to the power of x plus log base 2 of x through the point 2, 26. Use the exact value of the slope. Let's begin. Here, the derivative g prime of x is equal to the natural log of 5 times 5 to the x plus, and then the derivative of log base 2 of x is 1 divided by x times the natural log of 2. In order to compute the slope, that is m is equal to the derivative g prime evaluated at 2. That would be equal to the natural log of 5 times 5 squared plus 1 over 2 times the natural log of 2. In exact form, you would have 5 squared is 25, so 25 times ln of 5 plus 1 divided by 2 ln of 2. We have a point, that's 2, 26. We have a slope, 25 ln of 5 plus 1 divided by 2 ln of 2. Now we could put this in the equation form of a line, and the equation is 1 minus, for y1 we put in 26, equals, for the slope m, it'll be 25 times ln of 5 plus 1 over 2 ln of 2, and then that's times x minus x1, which would be x minus 2. We have some special derivatives rules of exponential and logarithmic functions. They are d dx of e to the f of x. Note that f of x represents a function. That is equal to the derivative of the function that e is raised to times e to the f of x. Make sure you know this by heart. And the d dx, or the derivative of the natural log of, and the argument is a function, f of x. This is equal to the derivative of the argument, that is f prime of x, divided by f of x. This is also something you need to know by heart. The process used here is called the chain rule. Example 1.8.9, find the derivatives of the following functions. A, g of x equals e to the negative x. Let's observe that this is the pattern of e raised to a function. That is, if we want d dx of e to the f of x, that derivative is the derivative of whatever e is raised to times e to the f of x. For clarity, let's observe that the f of x function here is negative x, so the derivative f prime of x would be negative 1. Then when we take the derivative g prime of x, we would have, for f prime of x, negative 1, and then times e to the f of x, which would be e to the negative x. So the derivative g prime of x equals negative e to the minus x. Let's do part B. H of x equals the natural log of the quantity x plus 1. The rule we just learned says that if you want the derivative of the natural log, whose argument is a function, that is equal to 1 over f of x times the derivative of f of x. So let's identify that for this function, the f of x is equal to the quantity x plus 1, and so the derivative f prime of x is just 1. Now we are ready to take the derivative of h of x. So h prime of x is equal to 1 over x plus 1 times the derivative of x plus 1, which is 1. And when simplified, h prime of x is equal to 1 divided by the quantity x plus 1. Let's continue with part C. Y equals e to the quantity x squared. Let's write that differentiation formula again. That is d dx of e to the f of x is equal to the derivative of f of x times e to the f of x. For this specific function, the power function, x squared, that's our f of x. And so the derivative of x squared is 2x. Now let's apply that rule. That is, y prime is equal to the derivative of x squared, which is 2x, times the original, which would be e, to the power of x squared. Now let's do part D. Y of x equals ln of x to the power of 4. I'm going to write that differentiation property again. That is d dx of the natural log of f of x is equal to 1 over f of x times the derivative of f of x. So in this problem, we will identify the function f of x, that's the argument inside, as x to the 4th. Then the derivative of x to the 4th would be 4x cubed. Now we're ready to find the derivative of y of x. So y prime of x is equal to 1 over the function, that's 1 over x to the 4th, times, then we have 4x cubed, that's the derivative f prime of x. When simplified, that's 4x cubed divided by x to the 4th, and it further simplifies to 4 divided by x. This exercise should look familiar. It is exactly the same exercise you did for 1.8.2 part A, except when we did it first, we used exponential properties, but this time we just used the new derivative rule. Part E, I of x equals 9 times e to the power of x to the power of 9. Let's take the derivative. We start with I prime of x equals constant times a function rule, so we'll have the constant 9 times. Now we will take the derivative of e to the power of x to the power of 9. The derivative, we start out by writing e to the x to the negative 9, and then we need to take the derivative, so I'll write d dx of x to the negative 9. Let's continue. 9 times e to the x to the negative 9 times, and now the derivative of x to the negative 9 would be, bring down the 9, then we have x to the power of negative 9 minus 1 would be negative 10. Let's clean this up just a little bit, and we would have positive 9 and negative 9 is negative 81. We have e to the x to the negative 9, and we can write the x to the negative 10 in the denominator as x to the positive 10. And one last problem for this lesson, f. Y equals the natural log of 6x squared plus 2x plus 2. Let's take the derivative. Y prime is equal to 1 divided by the argument, which is 6x squared, plus 2x plus 2. And the rule tells us we need to take the derivative of whatever was inside the parentheses, which is 6x squared, plus 2x plus 2. Let's continue. Y prime is equal to 1 divided by 6x squared plus 2x plus 2 times, and then the derivative of 6x squared, 6 times, bring down the 2, it'd be 12x, plus the derivative of 2x is just 2, and the derivative of 2, which is a constant, is 0. So the final cleanup could look like y prime is equal to 12x plus 2 divided by 6x squared plus 2x plus 2. Oh, look at that. There is a common factor of 2 in both the numerator and the denominator, so we can further simplify this to 6x plus 1. And for the denominator, 3x squared plus x plus 1.